So in the early 20th century, Rutherford's gold foil experiment helped to establish the answer to the question where are the positively charged particles, the protons, are found in the nucleus. So then the question shifted to where's the electrons going to be located? And so this question always takes me back to that famous Wendy's commercial from the 1980s, in which three old women are um, you know, ordering a sandwich and they're taking a look at this, they're admiring this sandwich, and then they take the bun off. And this little old lady in the lower right hand corner here, her name is Clara Peller, and she was actually responsible for catapulting Wendy's sales up into the region where they actually began to be able to become serious competitors with McDonald's and Burger King. So a little bit of nostalgia here to kick things off. I wanted to show you this age-old, timeless commercial.
It certainly is a big bun.
It's a very big bun.
Big fluffy bun.
It's a very big fluffy bun.
Where's the beef?
Some hamburger places give you a lot less beef on a lot of bun.
Where's the beef?
At Wendy's, we serve a hamburger we modestly call a single. And Wendy's single has more beef than the Whopper or Big Mac. At Wendy's, you get more beef and less bun.
Hey, where's the beef? I don't think there's anybody back there.
You want something better. You're Wendy's kind of people.
Okay, so again, to lead off this lesson, we ask the question, where's the electrons? So, to identify where electrons are at, we have a couple of different methods for that. One is in group, like all of them all together. We do that by way of orbital energy level diagrams and electron configurations. But we can also locate electrons specifically, each individual electron, through what are called quantum number sets. And quantum number sets is something that we'll look at in a different lesson. For right now, we want to focus on orbital energy level diagrams and electron configurations. So the first thing that we have to understand are the different levels of which we can place electrons. And the primary level, the first kind of biggest level, would be what we call the principal or main energy level. And this is sometimes represented by the letter N. We've seen this when we looked at the Bohr model of the atom. Within those main energy levels then, and we had evidence for this, for the existence of sublevels with emission line spectra. So sublevels are represented by the quantum letter L, and each sublevel, there's four different types of sublevels at this point, designated by letters, S, P, D, and F. And so each sublevel type contains different numbers of orbitals. So what are orbitals? Orbitals, which are represented by the quantum letter M, indicate the area of space, the physical area of space where two electrons are going to be located. Now, the type of sublevel that you've got, if it's an S sublevel, then S orbitals, their shape is going to be a spherical shape. Okay, and so what you get, what this cloudy kind of area here represents an area of highest probability where you're most likely to find electrons for an S orbital. And notice it's very much spherical in shape because with two electrons, they would essentially be on opposite sides of the sphere, inscribing this spherical shape. Now, whether you have a 1s sublevel, a 2s sublevel, or a 3s sublevel, or 4 or 5s, it doesn't matter. If it's an S sublevel, it's spherical. The number, which corresponds to the main energy level, tells us about what size it's going to be. So a 1s orbital is going to be a small spherical orbital shape, whereas a 3s orbital would still be spherical, it would just be larger. And so imagine these all overlapped on one another with the nucleus at the center, kind of like the layers of a jawbreaker, if you want to think of it that way, is what your different S orbitals would look like. P sublevels, right, can hold 3 orbitals. And so to get 6 electrons to occupy the same energy, you have to get a little more creative with the shape of the orbital clouds, and so you get what we call these dumbbell-shaped orbitals. And each of those three dumbbell-shaped orbitals lies along a different axis, right? One on the x, we call that the px orbital. One on the y, the py orbital, and then the pz orbital. D sublevels can hold 10 electrons, so that means 5 orbitals, and so you can see things start to get a little more interesting. You get these flower-shaped orbitals that usually lie in between the axes, and then you get this kind of strange-looking one here. And then F's, we're not even going to try and draw those. There are a total of 7 of those orbitals, and again, they get very strange-looking for the S. Or for the F orbitals. And there's one more quantum letter, the spin quantum number, that's represented by S. We'll talk about that in a little bit as we talk about the guidelines for distributing electrons. So the first guideline is what's known as the Aufbau Principle. The word Aufbau literally means filling up. And so just like if you remember playing the game Connect 4 as a child, when you drop a piece in, it falls to the lowest open position. And then when you drop the next one in, if that lowest position is filled, then it goes to the next open position. Electrons do the same thing. When you get to a sublevel where there is more than one orbital, so the 2p sublevel, when you have multiple energy or orbitals that are at the same energy, we say that those orbitals are degenerate. Okay, so the 2p level has 3 degenerate orbitals. And what Hund's rule tells us is, as we're distributing electrons into that 2p level, there's 3 orbitals, so it can hold up to 6. You put 1 electron in each of the open orbitals first. So the first electron would go in the first 2p orbital. The second would go in the next one over, and the third would go into the furthest one to the right. So you don't fill up the first block, then go to the second block, then the third. You divvy them out like you're dealing cards, 1, 2, 3, and then for 4, 5, and 6, you go back and you double them up. Okay. The second part of Hund's rule says that when you distribute those electrons, each to those empty orbitals, you have to put them in with the same spin. And practically speaking, that means that the arrows that we use to represent electrons all have to be pointed in the same direction. Conventionally, it's up for the first ones to go in, but it doesn't have to be, as long as they're all the same direction. Now, when electrons 4, 5, and 6 go in, that means you're going to have 2 electrons in the same physical area of space. Remember, electrons are all negatively charged, and so like charges tend to repel. So how do you get 2 similarly charged particles to occupy the same area in space and not repel each other? Well, if we think about electrons as little spinning spheres, okay, the magnetic field that they generate will be in a certain orientation, just like the Earth, as it rotates on its axis based on its molten iron core, generates a magnetic field. Well, if you were able to reverse the spin of the Earth, the magnetic field polarity would be switched. And, for instance, north would point down and south would be up. So when we talk about the spin of electrons, we think of those electrons as, spinning, one clockwise, one counterclockwise, and we refer to that as a spin up state and a spin down state. And what the last guideline tells us is that when you put 2 electrons in the same orbital, like electrons 4, 5, and 6, they need to be with the opposite spin. You have to draw them in with the opposite spin. So the Pauli Exclusion Principle says if 2 electrons are going to occupy the same orbital, they must have opposite spins. Now, when it comes to writing the ground state electron configuration for any element, first of all, when it says ground state, it means we're abiding by Aufbau. So as you can see, the electrons, right, we're filling in from 1s and 2s, and it's filling in as we go up here. And tin, how many do we need? Well, we find tin, and tin's got 50 protons, which means it also has 50 electrons. And so if we fill those in according to our guidelines, we see that we get all the way up to the 5p level. Not completely filled, but that's as far as we need to go to get 50 electrons distributed. So this is what we call the orbital energy level diagram. So diagram indicates a picture, so boxes and arrows. When it asks about electron configuration, this is the written summary of where the electrons are going to be. And to write the electron configuration, we write the different orbital notations. Okay, and that's going to consist of the main energy level and the sublevel letter, okay, followed by an exponent which tells us how many electrons are actually in that sublevel. So the configuration for tin would start out 1s, 2, and then the next lowest energy level we have is 2s, and it's got 2, so you'd have an exponent 2 there. Then 2p, 6, 3s2. You keep working your way up the table or up the diagram, and you get this big long string, okay, which now identifies the location of all 50 electrons for tin. You can add up the exponents to verify that you've got 50, okay? And so this is how you would go about writing the electron configuration for any element on the periodic table. And you can use this diagram here, as a template to help you determine the proper order for filling in those sublevels. So at this point, you should go to the next page, the applications of electron filling guidelines. And so this first section, this first example, gives us 3 different proposed answers given to a prompt. Provide an orbital energy level diagram for the ground state of a nitrogen atom. Okay, and what you see here are 3 sample answers. Your task, okay, is to, you and a partner, okay, you're going to pause the video, you're going to pick a partner, and then you and your partner are going to look at those 3 proposed answers. And first of all, determine, are they correct as drawn or not? And if not, then explain why they're incorrect. Once you and your partner have done this, you can go ahead and resume the video and check your answers. All right, so looking at the first one, hopefully you and your partner determined that this one is incorrect. All right, and it's actually incorrect for 2 reasons. As far as the guidelines go, Aufbau is the principle that is being violated here. Because remember, Aufbau says you fill in the lowest energy level orbitals first before you move to higher energy orbitals. Well, right here, okay, the 2s orbital is not completely filled up. So we should not be putting electrons in 2p, much less the 3s orbital. Okay, so that's the first thing that's wrong. The second thing's a little more subtle. If you count, you've got 1, 2, 3, 4, 5, 6 electrons shown. But the prompt was asking us to draw the orbital energy level diagram for a nitrogen atom, which has 7 electrons. So there's not even enough electrons or arrows shown in this orbital diagram. Looking at the second example, okay, it looks a little unconventional, but even though it's unconventional, it doesn't mean it's incorrect, right? This would be permissible, okay, according to all the guidelines. You have no empty orbitals, okay, so we're not violating Aufbau. The 2p orbital, you have degenerate orbitals, and you've got 1, 2, an empty orbital first before anything pairs up, and they are all in the same direction spin. It may be unconventional because typically the first arrows we draw would be up, but as long as all 3 are consistently drawn in the same direction, everything's okay. The last example, again, hopefully you indicated that that was incorrect. The problem with this one is it's violating Hund's rule, specifically the fact that here you have 2 electrons in this first 2p orbital, and then down here you have an empty 2p orbital. So there should not be pairing of electrons while there's an empty orbital available. So now that we've talked about how to distribute electrons in the different locations that we can describe them in, what I'd like you to do is to pause the video, and for each of these 3 elements, sulfur, silicon, and neon, based on how many electrons they've got, fill in the arrows, abiding by those electron filling guidelines. Fill in the arrows, and then after that, summarize the sublevels and the electrons that they have in them in an electron configuration, and you can write that in these boxes down below. Okay, so again, just a reminder, when we say ground state, that's telling us that we're obeying the Aufbau Principle. That's what that means. Orbital energy level diagram, that's your boxes and arrows. And then electron configuration would be these codes down here, the 1s2, 2s2, and all of that. So pause the video, give these a shot, and then resume the video and check your answers. All right, so for sulfur, this is what your distribution should look like. And this would be your configuration. For silicon, this would be your orbital diagram and your electron configuration. And finally, for neon, with its 10 electrons, all right, you would have this orbital energy level diagram and this configuration.